Hi, and welcome back. This is the second video for Chapter 3. Now, in the previous video, I talked about the link between um, the macroscopic view of the world, that is, you know, uh, observables like temperature, volume, mass, pressure, and how they're related to the microscopic realm. I also derived for the ideal gas law a relationship between temperature and kinetic energy. Now, today, what I'd like to do is to talk about the next order approximation to gases. So, if you remember last time, I had come up with two versions of the ideal gas law. The one that physics likes to use looks like PV is equal to capital N K sub B times T. And then you have the one that chemistry likes to use, which looks like PV is equal to lowercase n times R times T. And, this is the Boltzmann constant. And this right here is the ideal gas constant. Now, so that said, I mentioned last time some of the assumptions that are made with respect to what we think of an ideal gas as being. And the primary things is that your gas molecules, for the most part, have no volume. So your gas particles are points. And plus, more importantly, your gas particles do not interact with each other. Now, so what that means is that if you were to think of, again, and this is just a two-dimensional cross-section of a box filled with gas particles, and let me put some gas particles in here. So there's your gas particles right there. That, as these things move through, you could have them collide, but during the collision process, they're not interacting, so they just sort of pass through each other. So what that means is that a gas particle is able to go from one side of the box to the other side of the box um, freely with no interaction. Now, this is all fine and well, but these two observations right here do not actually agree with reality. However, as we've discovered, the ideal gas laws actually do a really good job at describing the behavior of gases. So, what if you want to do an even better job? Well, there are a few things that we need to change in the ideal gas law, and I want to look at this one right here. This is the one we're going to be using to do this, just out of convenience. So, so here it is. Here's your ideal gas law. And the first thing I'd like to point out is that our gas particles are not little points, they actually have a volume. So each particle of your gas has a volume. Now, if you think of them as being little hard spheres, which is what we're going to pretend, okay, little hard spheres, they have a radius. And so, the volume of a gas particle would look something like, 4/3 pi times r cubed. Okay. Now, so we're not going to make any guesses as to what the individual volume of a gas particle is. This is something that we would solve, we'll say, empirically for. And there are some things that you can do to theoretically get it. But what that means is that if you think of your gas particle going from here to here and back, that the space, the volume that is traveling through, isn't just this big free volume. It's this big free volume minus the volume of all the individual gas particles that there are. Okay. So it's actually traveling through less volume than what you would expect because the other part is occupied by the actual matter. Okay. Now, so to sort of, I guess, put that into form, what I'd like to do is to divide both sides in this equation by V. So on the right-hand side, I have nRT divided by V. And so here, what I'd like to do is to define something called the molar volume. If you take the volume of your gas and you divide it by the number of moles, this usually is something that we call V sub m, okay? And it's basically the volume per mole of your gas, okay? So you have N over V for, our molar volume. And if you look at our equation here, in the denominator you have a V, in the numerator you have an N. So you can rewrite this as RT divided by V sub m. Now, the next thing I'd like to point out is that this volume right here, well, that's not really what our gas is working in. Again, we have to take into account all of the individual volumes, if you will, of our little gas particles that are in there. Now, we're just going to call that amount B. Okay, so B here would be the volume occupied by all of the individual gas particles per mole, because I wanted to have the same units as this. So in reality, this is going to turn into this minus B. And this, like I said, is the volume that makes up, or that is occupied by, all of our little individual gas particles per mole. So now our gas law looks like this. Okay. Now let's talk about the pressure. So the pressure, if you remember arguments from last video, is a consequence of the impacts that happen on the walls of the container. But when you add in the fact that your particles are not in fact points, but actually have volume to them, and you allow them to interact with each other, we'll say just through simple collision. That's the first order approximation, is simple collisional interaction. What you'll discover is that this pressure right here is a drastic overstatement of really what's going on. And the reason is because each collision is going to take away some momentum. Okay? Now, not only that, because you're taking away some of the momentum, there are going to be fewer collisions. Okay? Now, so what that means is that our pressure over here is an overestimate as to what the pressure really would be. So what you would have in order to make this sort of equal would be you would start off with your ideal gas pressure and you'd have your real pressure. And then what you do is you take and you would subtract away from the ideal gas one the what's the best way to describe this? The loss due to internal collisions. Okay. Now, so what does this loss look like? Well, each one of these things right here contributes to it. And they both, it turns out, contribute in the same way. So if you think about it, the number of atoms that you have, or the number of moles that you have, that occupies a volume of space, is going to dictate how often you see collisions. Okay. We know 1 mole is 1 Avogadro numbers of particles. So the more particles you have, the more frequently you're going to have collisions between them. That also means that you're going to experience that many fewer collisions against the container walls. So this pressure right here, due to the collisions and stuff, is going to be proportional to the number of moles per volume for this one, and also the number of moles per volume for this one. Now, typically, and this is really the only proportionality that we're going to have in this approximation, typically what we do is we put an equal sign, and we're going to put an A there as our little parameter. And then you have N over V squared. So, like I said, in reality, our ideal gas pressure is a combination of what's really going on plus the losses that you have. Okay. So I'm going to call, just for sake of convenience, if you will, P here, I'm going to call the real P. Okay, the real pressure is P. So on the left-hand side, now what I have is the real pressure plus A times N over V squared. And on the right-hand side, I have R times T divided by the molar volume minus the volume occupied per mole of all the particles that are there. Now, what I'm going to do next is to take and move this to the left-hand side. And when I do that, I get P plus A times N over V squared times V sub M minus B is equal to R times T. Now I want to multiply both sides by N, the number of moles. And I specifically want to pull the N into these two right here. You'll remember up here that the molar volume is V over N. So if I multiply this by N, I get the original volume back. And that puts an N beside this. It also puts an N out over here. So we have P plus A N divided by V squared is equal to, or rather it's not equal to, sorry about that, times V minus B times N is equal to nRT. Now, so this is the first correction that you would really make to the ideal gas law in order to get things to agree a little bit better with experiment. And this has a name. It's called the van der Waal equation. Oops. Okay. Now, so just as an example, let's pretend that you have 1 mole of CO2 and that it occupies 5.36 times 10 to the fourth cubic meters, and it sits at a temperature of 373 Kelvin. What I'd like to do is to find out what the pressure is according to the ideal gas law, and then find out what the pressure is according to the van der Waals equation. Now, for CO2, you can look up the values of A and the values of B, but typically these are chemistry values, and so they're expressed in things like atmospheres and liters. Now, we're going to need to convert, knowing that there are 1,000 liters in 1 cubic meter, and that 1 atmosphere is 1.01 times 10 to the 5th pascals. Okay, so here's what we're given. N is equal to 1.00, 1 mole. Our volume is 5.36 times 10 to the 4th cubic meters. The temperature is 373 Kelvin. A, which is one of our constants here, is 4.61. It's liters squared atmospheres divided by mole squared. and B is equal to 0.0428 liters per mole. Now we're going to need to convert these here. So for part A, we're just trying to find the pressure using the ideal gas law. And so let's go ahead and do that one. That one's pretty easy because we know that PV is equal to N times R times T. So if we want the pressure is just going to be nRT divided by V, the volume. So N is 1.00 moles. Excuse me. R is 8.31. Let me make sure that's correct. For some reason, I'm thinking 1.3. Just to make sure here. 8.31, yeah. So 8.31 joules per mole Kelvin. The temperature is 373 Kelvin. And our volume is 5.36 times 10 to the fourth cubic meters. So let me open up my calculator here. Give me a second here. Let's see. Excuse me. So it is 8.31 times 373 divided by 5.36 times 10 to the fourth. Now I get a pressure of 5.78 times 10 to the minus second pascals. Okay. Now, what about for the van der Waals equation? Well, remember, the van der Waals equation looks like this right here. So since it's more complicated, let's copy that. Then I'm going to come over here and we'll paste it. So here's our van der Waals equation right there. So for it, we want to find the pressure. So our equation looks like P plus A times N over V squared times this stuff, all the stuff here on the right-hand side. I'm going to start by moving this over to the right-hand side. So on the left-hand side, you have P plus A N over V squared. On the right-hand side, you have nRT over V minus B times N. So we want to find P. That's just going to be nRT divided by V minus B times N. And then we're going to subtract away, that bit of pressure there that's due to the interactions. Now, remember, in order to do this, we still need to do some conversion here. So let's just go ahead and convert this right here. Let's see. The easiest way to do this, because it's a little messy here. Let me just snag these real quick. And what I'm going to do, well, I'll tell you what, I don't even need to do that. I'll just write it down here. A is equal to 4.61 liters squared times atmosphere divided by moles squared. Now, we don't need to do anything with the moles because, that's going to be handled here. But what we do need to do is to handle the liters and the atmosphere. So if you think about it, we know that there are 1,000 liters per cubic meter. So for every liter, we have to divide by 1,000. to get rid of it and put cubic meters there. So we have to do that twice because there's two of them. And then we have an atmosphere. And we know that there is 1.01 times 10 to the fifth pascals for every one atmosphere. So when you do this conversion here, let's see. You have, let's see, 4.61 times 1.01 times 10 to the fifth. And then I need to divide that by 1,000. But I got to do that twice. And so for this right here, I get 0.46561. I'm going to put this in weird units, I guess. Meters to the 6 pascals divided by mole squared. That's what it is, though. All right, so for B, that's pretty easy. That's equal to 0.0428. It's liters per mole. So again, we know that 1 cubic meter is 1,000 liters. So really just dividing it by 1,000. So when you do that, that's going to end up being 4.28 times, let's see, there's 2, 3, 4, 5, 10 to the minus fifth cubic meters per mole. All right, so let's see here. Okay, so now let's do this. Okay, so our pressure is going to be the number of moles, 1.00 moles. You've got an R. R is 8.31 joules per mole Kelvin. You have your temperature, which is 373 Kelvin. Then you have to divide that by the volume. The volume was 5.36 times 10 to the fourth cubic meters. And then I have to subtract away B times N. That's 1 mole times B. And B was, 4.28 times 10 to the minus fifth cubic meters per mole. So I would like to point out the units here. You have cubic meters because this is a volume. Clearly, you can see here the moles are going to cancel, giving you cubic meters. But what I would like to point out is that this is operating around the fifth decimal place. So when you subtract away this tiny amount of volume, it's not going to really appreciably change the pressure. But we still have this additional term here, right here. And I suspect it's going to be very tiny too, but let's just see. So this is going to be A, which is 0.46561 meters to the 6 pascals divided by moles squared. And then I have N over V, and I got to square that. N was 1 mole, and V again was 5.36 times 10 to the fourth cubic meters. So again, I would like to point out that when you square this cube here, it becomes to the power of 6. So those cancel. Your moles are going to cancel because that's squared, and you end up with pascals, which is what you want. But look, down here in the denominator, this is affecting things around the eighth decimal place, basically. So we're not going to see an appreciable difference between this pressure right here and the pressure that you get, through the ideal gas law. But let's just see what we get. This is 8.31 times 373 divided by 5.36 times 10 to the fourth. And then I have to subtract away the 4.28 times 10 to the minus fifth. So there's our first term. And then we're taking away, like I said, the pressure that's a consequence of collisions and, against each other, and plus the decreased collision frequency. And that ends up being about 0.46561. And then we have to divide that by 5.36 times 10 to the fourth. Whoops. Let me backspace that here, because 5.36. Made a typo there. Times 10 to the fourth. There we go. That's better. All right. So you square that, and you end up with 0.578. 0.0578 rather. So, I mean, if you take a look here, it's the same. This is 5.78 times 10 to the second. But let me just, out of curiosity, write this all the way out. So I get 0.0578289,178 using this. But if I were to go back and to take a look at the previous calculation, get to that here. This is from the other one. 0.0578289,179 pascals. So there's something going on out here that's a consequence of this small collisional thing going on here, and also the decrease in volume. Now, where are you going to see this effect really rear its head? Well, when you have a higher density gas. For example, you've jammed a lot of gas into a small volume, then what that does is to increase this substantially, because you're increasing the number of moles. And it also causes this to go up as well, because now your volume is smaller, but the number of moles that you have is bigger. So that's where you're going to really see this effect. Okay, so like I said, this van der Waals equation right here is the first approximation that you make to the ideal gas law in order to make it more correct. Now, there are other approximations that you make, but we're not going to cover those in this class. Those are better left to a full-blown thermodynamics class, typically seen at the graduate level. Now, that said, since we've introduced the idea of collisions, what I would like to do is to talk about the idea of what's called mean free paths and mean free times. So if you're letting these things collide, as this thing goes through and hits a neighbor and has this path deflected like this, there is an average distance in your gas that a particle would have to travel to hit a neighbor. So that distance is called the free path. How far can a particle freely travel before it collides with a neighbor? But because it's an average, and another word for the term average is mean, we're talking about the average or the mean free path when we talk about the properties of a material or a gas, if you will. Now, the mean free time is not how far, but how long. Okay. So you could think of the mean free time as an expression of how frequently collisions happen. So, if you think about it, let's pretend that you have what's the best way to describe this? So let's pretend that you have some sort of area that you're sort of watching. So you got a sensor that's just watching this area here. And so what you're going to do is you're going to throw a particle through here and hanging around somewhere in here. You have another particle. Okay, somewhere around in here. Now, statistically, how likely this thing is to pass through and hit that particle is going to depend upon the area that it's traveling through and the area of one of the particles. Now, if you think about your particle as having a radius, we'll say of r. So here's our little particle right here. He's got a radius. Then the cross-sectional area, okay, that is the area presented to something flying through that it may impact, would be equal to basically the area of a sphere. Okay? So, the area of a sphere is 4 pi r squared. Now, if I think about how frequently these things may fly through and hit neighbors, the total area of all the molecules present that I could hit would be the number of atoms that are there, or molecules, times the area of one of these that might be available. Okay? So if I were to think about this now, not so much as just being an area, but being a volume, it has a depth, which we'll call L. Then, how far one particle would need to go in order to hit a neighbor would be that volume divided by the area of all the molecules that are there saying, you can hit me. Or the volume divided by the number of particles times 4 pi r squared. Now let's talk about the actual motions of these things as they flit around. So, if you think about this as being, one of our particles and this as being another particle of gas, the truth of the situation is that these things are going to be flying around like that. So, they're going to have full three-dimensional motion. I'm going to call this particle 1. This is particle 1's velocity. This is particle 2. This is particle 2's velocity. Now, a lot of times, what we do is to set things up so that we look at just the collision aspect. So you'll notice that this has an upwards component. You'll notice that this has a downwards component. It's the side-to-side stuff that's really involved in colliding for the most part. So if you were to think of it sort of like this, whoops. If you put them sort of tip to tail, I don't want that actually. I want it like this sort of. Then this right here actually describes the towards each other motion. Now, we call this a relative velocity. And this is what we're interested in. So if this is V2 and this is V1 right here. Really, VREL is what you get when you take and you subtract V1 from V2. So if you were to flip V2 around, make it negative, then this plus this would equal to this. So that's the reason why it works that way. So it's this right here on average, because the motions of these particles on average are a measure of the temperature, right? And so the goal here is to find some expression for this relative velocity and then integrate this into this collision, because how fast these things move through is also going to affect how far they can go, and also the mean free time for collisions. So again, one way you can figure out this VREL, at least in magnitude, because that's what we want, is to take the square root of it dotted with itself. So, the length of a vector you can find by taking the square root of a vector dotted with itself. It's basically the Pythagorean theorem, okay? And so what we're going to do is we're going to take the square root of this thing, and what's being dotted is V1 minus V2. So this right here should be VREL in magnitude. I'm going to write without the vector as magnitude. So let's complete the square root right here. And so if you do your dot product, V1 dot V1 is V1 squared. V2, negative V2 dot negative V2 is going to be V2 squared. And then you're going to have a minus 2 V1 dot V2. Now let's talk about real properties of gases. Remember, this is statistically random motion. And if you were to look at all of the behavior of all of these things, this dot product is going to average out to 0. Okay? If you look at all of the behavior of all of the things, our VREL, really, V1 and V2 on average are going to be the same. So these right here, because of the motions, are going to average each other out. And these right here end up being just V. And you have the square root of V squared plus V squared, which is the square root of 2 times V. So if we go back over here, and I take this right here, and this right here is the mean free path, or at least it's related to it. We need to put in the reality of the motions of the particles in here. We're going to do that here in a moment. So it looks like this. Now, let me remind you something about the ideal gas law. The physics version looks like this. So I could manipulate this a little bit and solve for V over N. And all that is just K sub B times T over P, which means my mean free path, like I said, it's almost, we haven't taken into account the actual true behavior of the motions of the particles yet, is just K sub B times T over 4 pi R squared times P. Now, there's a square root of 2 here that is a consequence of the motions of stuff. So typically what's done is we take this and we put that square root of 2 down here. And if you do a full true derivation for this, which we sort of have to hand wave our way through this, unfortunately, there is a square root of 2 here that is a consequence of the fact that this is averaged motion. Now, so this is a distance. This is a speed, okay, or your RMS speed. So we know that distance is equal to speed times time. So if this right here is the true distance a particle would have to travel on average to go from point A to point B and experience a collision there, then the amount of time would just be lambda divided by VRMS. Or K sub B T divided by 4 pi r squared, square root of 2 times P times the RMS velocity. This is the RMS velocity right here. So, so now what we have is an expression that tells you how far a particle would have to go before it hits a neighbor, and also how long it would take for it to travel that far and hit a neighbor. And this is all based off of, again, uh, the ideal gas law and collisions through a volume. All right. So, as an example, what's the mean free path and time for helium at the sun's surface? The sun's surface temperature is 5,800 Kelvin. Helium has a radius of about 31 times 10 to the minus 12 meters. That's about 31 picometers. And the pressure at the surface is 1% that of the Earth's atmosphere at sea level. Okay? So what we've been given here, what we've been given here is a temperature, a pressure. Go ahead and write the radius down first, though. So a radius, a pressure, which is 0.01 atmospheres. Now, if you think of 1 atmosphere as being 1.01 times 10 to the 5th pascals, this right here is 10 to the minus second, or 1 to the minus second. So this would be the same thing as about 1.01 times 10 to the 3rd pascals. Okay. Now, what we're trying to find here is the mean free path lambda and also the mean free time tau. So the mean free path, if you remember, was K sub B times T divided by, excuse me, 4 times the square root of 2 times pi r squared. Okay. So Boltzmann's constant, if you look that up, I want to say it's 1.38 times 10 to the minus 23rd. Wrong there. It's one of those that I never remember. Yeah, that was right. 1.38 times 10 to the minus 23rd joules per Kelvin. T here is 5,800 Kelvin. We have 4 square root of 2 pi, and then we have the radius, which is 1.01 times 10. Oh, what am I saying? Well, there's also a pressure here as well. What am I saying too? Because there's a pressure, so may as well put that in. 3rd pascals. Now let's put this in, the radius. 31 times 10 to the minus 12 meters. You guys square that. So let me put this into my calculator over here. Let's see. 1.38 times 10 to the, let's see, that's 23rd. times 5,800. And then I have to divide that by 4 times the square root of 2. Oops. Let me delete that real quick. Just made a mistake. There, that's better. All right, 4 times square root of 2 times pi. And then times 1.01 times 10 to the third. And then I have to multiply that by 31 times 10 to the minus 12th. And then I got to square that. And that is 4.64 times 10 to the minus third meters. So something like 4.6 millimeters is how far a helium atom can travel basically through space at the photosphere, which is the surface of the sun, before it hits a neighbor. Now, that's actually pretty far, and the reason why it's pretty far is because your gas is low density, and also because it's high temperature. Okay. Now, so let's do the time. Now, really, the difference between the distance and the time equation is a factor of VRMS in the denominator. And VRMS comes from this. Okay, so remember, this is VRMS. Okay. So let's just go ahead and find VRMS, noting the fact that the mass of a helium atom is 4 atomic mass units, or 4 times 1.66 times 10 to the minus 27th kilograms, or 10 to 10 to the minus 27th kilograms. That's right. So let's see here. 4 times 1.66 times 10 to the minus 27th. This is going to be 6.64 times 10 to the minus 27th. So that's our mass. So now it's just finding VRMS. We'll go ahead and cancel out the halves there real quick. And VRMS is going to equal to, the square root of 3 sub b times t divided by m, or 3 times 1.38 times 10 to the minus 23rd joules per Kelvin times 5,800 Kelvin divided by 6.64 times 10 to the minus 27th kilograms. So, if you solve for this, this is, let's see, the square root of 3 times 1.38 times 10 to the minus 23rd times 5,800, and divided by 6.64 times 10 to the minus 27th. And I get 6,013. So now, our mean free time here is going to be lambda divided by VRMS, which is going to be, 4.64 times 10 to the minus third meters divided by 6,013.54. So 4.64 times 10 to the minus third divided by 6,013.54. And that is 7.71 times 10 to the minus seventh. So this right here is the average time it takes between collisions. And you could actually talk about the collisional frequency here just by taking that and dividing 1 by it. Because, frequency is 1 over the period. This would be like a collisional period. Now, so the very last thing I'd like to talk about is heat capacity and energy equipartition. Now, so heat capacity we've kind of already seen before. If you remember the first chapter, we were talking about macroscopic quantities. I talked about how when you have a pure phase, a solid, liquid, or gas that's not undergoing a phase transition, that you can relate the amount of heat that you add into something to its specific heat, its mass, and the change in temperature. So this is specific heat. But as we talked about so far in this chapter, we know that sometimes the mass isn't really something that you'd like to talk about. Sometimes what you'd like to talk about would be the number of atoms or the number of moles, like, for example, the chemistry version of the ideal gas law. So you can rewrite this, and there are a couple different types of these heat capacities, is what they're called. This one right here is for constant volume. We'll talk about the constant pressure one later on when we talk about the first law of thermodynamics. So when you have something that's fixed in volume, what that means is that your gas inside here isn't allowed to expand beyond its volume. So if you think about places in which energy could go, and I've mentioned this once before, I believe, is here when you add this heat in, this heat is going into causing a change in temperature. But let's pretend that you had a balloon that could expand. Well, then, because it expands, it actually can do work on the environment, and you can add in a work term as well. Now, we'll be doing that when we talk about, again, the first law of thermo, but we're not going to do that right now. So anyway, at a constant volume, you have our simple relationship that we've seen so far when dealing with solids, liquids, and gases that are undergoing, changes in temperature as a consequence of heat. So what we say is you add your heat in, and what that does is to cause your gas, which instead of talking about how much mass your gas has, we're going to talk about how many moles it has, to experience a change in temperature. Now, in this case, because we're dealing with moles and not mass, we don't call this the specific heat. We call this the molar heat capacity. And we use a capital C for it. And to show that it's something that was derived under the assumption of constant volume, we put a little v here. So there's this C sub v thing here called molar heat capacity. Okay, so now I want you to think back to our previous video where we talked about the kinetic theory of heat, basically. And I said that 1/2 mvrms squared is equal to 3/2 k sub b t. Now, this is for one particle, right? So if I wanted to know the total average kinetic energy, okay, the total kinetic energy, which I'll call E, what I would do would be to take this and multiply it by the number of atoms that I have. So if on average each one has this amount of energy, if I have n atoms, I'm going to multiply it by n. So it would be, in that case, 3/2 n k sub b times t. Now, so here's the deal. The heat that I add is going to be equal to this. I add this heat in. It causes the energy to change on the inside, the temperature to change. This is how much energy is on the inside. So what this does, what Q does, is to cause a corresponding change in energy inside the gas. Now we use U for what's called internal energy. Internal energy. And it's the same thing as this. It's basically your, at least initially, your change in kinetic energy on the inside. Now, when you have phase transitions, we can also associate it to that. So, but right now, we're just going to consider situations in which you add heat and you just have a change in temperature, like I said, a pure phase. So what that means is that my heat here, which is C sub V times N times delta T, is also equal to 3/2 capital N, this is number of atoms, K sub B delta T. But remember, if you look at the ideal gas laws, both the physics version and the chemistry version, there's a relationship between N K sub B and the number of moles times the ideal gas constant, and it's that right there. So this right here is the same thing as N times R. So on the left-hand side, C sub V, N delta T. On the right-hand side, 3/2 N times R times delta T. That goes away. That goes away. And what we have is that as long as your gas, your ideal gas, is kept at a constant volume, its molar specific heat, or molar heat capacity, is equal to 3/2 times R. Now, we treat all gases the same. Remember, hydrogen, helium, whatever, they're all treated the same. So this is, in general, for an ideal gas, what your molar specific heat, or your molar heat capacity, is going to be. Now, that said, let's talk about energy equipartition. Specifically, I want to look at this 3/2 sitting out in front. And I'd like to remind you that that 3 got there through this. And the 3 got here through looking at motion along the x direction, motion along the y direction, and motion along the z direction on average. That is, 1/3 of the energy was along x, 1/3 of the energy is along y, and 1/3 of the energy is along z. Now, x, y, and z are directions that you can move. We call them degrees of freedom. So, in general, what's the best way to write this? I'll put a d over 2 times r, where d is the degrees of freedom. Now, here, a degree of freedom means where can I put energy? Okay? I can uniquely have motion along X. I can uniquely have motion along Y. I can uniquely have motion along Z, which means that for a gas in which you don't consider any sort of inside places where you could hide energy, or its behavior as it goes from point A to point B from a rotational standpoint, you have three, which makes that three halves. They are partitioned off. One partition in X, one partition in Y, one partition in Z. Now, that said, imagine a gas that instead of being monatomic, might be diatomic. Okay, so it's made out of two molecules. As it goes through space, maybe it rotates, maybe it vibrates. And those are two unique places in which you can take and you can put energy, which means that D increases, which means that your molar specific heat is going to change because you have more places in which you can hide energy. Now, so that's what's meant by energy equipartition. And in the next video, I'm going to explain to you a little bit more about how the word partition sort of arises. And I'll see you then.